A robotics company called Droidup just unveiled a humanoid robot named Moya. But this isn't another robot that looks human and moves like a machine. Moya is built on a different principle entirely. It's designed to move, respond, and interact more like a biological system. That's what biomimetic means, mimicking human biology, not just human shape. In this video, we're breaking down what makes Moya different, why that matters, and how a recent breakthrough in flexible AI chips helps explain where this technology is actually headed. Droidup, a robotics company based in Shanghai, unveiled Moya at a major tech event in China in late 2025. The company describes it as the world's first fully biomimetic embodied intelligent robot. That's a specific claim. It's not just marketing language, it's describing a design philosophy. What Droidup showed was a robot that stands 1.65 meters tall, about 5 feet 5 inches, and weighs roughly 32 kilograms or 70 pounds. Those proportions are deliberate. It's built to match average human scale and proportions in the torso, limbs, and overall posture. But the proportions alone don't make it biomimetic. What biomimetic actually means here, biomimetic design means copying biological systems. In this case, human movement and physical response. Moya is built to move like a human moves, not just mechanically walk from point A to point B, but reproduce the subtle motion patterns that humans use naturally. In demonstration videos, Moya displays several specific behaviors. It makes sustained eye contact. Its facial expressions include micro-expressions, those tiny movements around the eyes and mouth that humans read unconsciously. It nods and reacts during conversations. It walks with a gait that has been designed to match human walking patterns with 92% accuracy according to Droidup's claims. That 92% figure is important. It's not measuring whether the robot stays upright or completes a walk. It's measuring how natural the motion looks and flows. A lot of robots can technically walk. Very few walk in a way that looks fluid and human-like instead of mechanical and jerky. Droidup built Moya with body temperature regulation. The robot maintains a surface temperature between 32 and 36 degrees Celsius. That's roughly 90 to 97 degrees Fahrenheit. That's intentional. When you interact physically with a robot, if it feels like cold metal or plastic, the interaction feels different. If it feels warm, closer to a living person, it changes how comfortable people feel around it. The robot's hands and arms are designed for dexterous manipulation. It can handle both delicate and bulky objects. The movements of the hands aren't just mechanical gripping. They're designed to move fluidly, matching how a human hand would approach and grasp objects. The head has a dynamic display system that changes expressions during communication, not just a static face. Expressions that update and respond. Most humanoid robots built over the past decade, Boston Dynamics Atlas, Tesla's Optimus prototypes, other industrial humanoids, use rigid joints and servo motors. The movement works, but it's optimized for efficiency and control, not for mimicking biological motion. When a traditional humanoid walks, you can see the mechanical nature of the motion. The joints move in isolation. The gait looks computed rather than natural. It's designed to be stable and predictable, which is useful for manufacturing or industrial tasks. Moya is designed differently. The goal is not maximum efficiency, the goal is biological realism. That means smoother transitions between movements, joint movements that coordinate with each other more like human muscles do, a gait that looks like a person walking, not like a machine executing a walking algorithm. This isn't about aesthetics or making robots look friendly. It's about how the robot interacts with its environment and with people. A robot that moves naturally integrates better into human spaces. A robot that moves mechanically requires people to adjust how they interact with it. The biomimetic design works because of advances in how the robot perceives and responds to its environment. The robot uses cameras for vision, microphones for audio, and presumably tactile sensors for touch. The AI system interprets what it sees and hears and generates responses that are natural and contextual. This is different from a pre-programmed robot. Moya isn't following a script. It's responding dynamically to what's happening around it. When someone makes eye contact, it responds with eye contact. When someone speaks, it responds conversationally and contextually. When it moves through space, it adjusts its movement based on what's in front of it. That requires AI that can process real-time sensory input and generate appropriate responses. It requires the kind of large language models and vision systems that have advanced significantly in the past few years. Industrial, robots work great when the environment is controlled. A robot arm on a factory floor works with parts that are exactly positioned. A robot in a warehouse works with boxes that follow predictable dimensions. But put a rigid robot into a human environment, a hospital, a home, a public space, and problems emerge immediately. Humans navigate complex, unpredictable spaces. We move around obstacles. We adjust our walking speed based on crowd density. We recognize when someone is uncomfortable with our proximity, and we adjust. A mechanical robot with rigid joints and computed movement patterns struggles with that flexibility. The other problem is safety. When a rigid robot moves, it moves with the precision of mechanical control. If it's moving at 3 meters per second and encounters a person, it doesn't naturally slow down or yield. It stops or crashes. A robot that moves biologically, that has fluid, adaptive movement, can modulate its motion in response to people around it. When a human reaches out to touch something and realizes it's hot or sharp, the hand automatically recoils. That's a biological response built into the nervous system. When a human walks down a crowded hallway, the gait adjusts unconsciously to match the crowd's rhythm and density. These aren't conscious decisions. They're embodied responses. A biomimetic robot designed to move like a biological system can incorporate similar adaptive behaviors. Not true reflexes, but computationally modeled responses that approximate how biology handles dynamic situations. This matters for industries where robots work around humans. Healthcare facilities where robots assist with patient care, service industries where robots interact with customers, public spaces where robots navigate crowds. Hospitals are interested in robots that can move smoothly through corridors without startling patients. Logistics companies are interested in robots that can work alongside human workers in warehouses. Service companies are interested in robots that can deliver food or packages in public spaces without triggering discomfort or fear. These aren't theoretical interests. Companies are actively seeking robots that can integrate into human environments without requiring the environment to be redesigned around the robot. A rigid industrial robot requires safety cages, limited access, and controlled movement. A biomimetic robot designed to move naturally can work in open spaces with minimal additional safety infrastructure. The value of biomimetic design isn't about making robots that are more human-like for aesthetic reasons. It's about making robots that are more compatible with existing human spaces and easier for humans to interact with intuitively. When a robot moves in a way humans find natural, people don't need to learn special procedures for interacting with it. When a robot responds contextually instead of mechanically, the interaction feels less like operating a machine and more like working with a tool that understands what you're trying to do. That compatibility reduces training time, it reduces friction in deployment, it reduces the need for environmental modifications. In parallel with advances in robotic design, researchers in China recently demonstrated a fully flexible AI chip. This chip contains approximately 10,628 transistors and is designed to bend, flex, and operate even when physically stressed or deformed. This is a recent breakthrough because traditional silicon chips are rigid. They work great when they're flat and stable on a circuit board, but they're fragile. If you try to bend a silicon chip, it breaks. If you want to integrate electronics into a flexible material, like a robotic skin or around a joint, rigid chips create problems. A biomimetic robot needs electronics distributed throughout its body, sensors in the skin for touch, processing elements near the joints to control movement, processors in the hands for dexterous manipulation. With traditional, rigid chips, you end up with a complex network of wires connecting separate rigid components. Flexible AI chips change that. You can embed processors directly into materials that flex and move. You can integrate sensors into the robot's skin without creating stress points or failure zones where rigid electronics meet flexible materials. This allows for more natural movement because the electronics follow the movement instead of constraining it. A flexible chip in a robot's arm can bend with the arm. A flexible chip embedded in artificial skin can flex with the skin. The key advantage is integration. Instead of bolting rigid components onto a flexible robot skeleton, you can embed flexible processing elements directly into the structure. This reduces weight, it reduces the number of connection points that can fail. It allows for more sophisticated sensor arrays distributed throughout the robot's body rather than concentrated in specific locations. The flexible chip demonstrated contains approximately 10,628 transistors. That's not a large amount of processing power. It won't run a large language model, but it's enough for local processing, sensor interpretation, basic decision-making, motor control. That's exactly what you need distributed throughout a robot's body. The larger language models and complex reasoning still happen in more powerful processors. But the distributed flexible processing handles the low-level sensory motor control that makes movement fluid and responsive. Biomimetic robots are only possible with advances in both software, AI models that can generate natural responses, and hardware. Flexible AI chips represent the hardware piece of that puzzle. Understanding that piece helps explain why biomimetic robots are becoming feasible now, even though the concept has existed for decades. The combination of advanced AI software and flexible hardware enables the integration of intelligence throughout the robot's body instead of concentrating it in a central processor. That distributed intelligence is part of what makes the movement and response more naturally human-like. Moya represents a step forward in biomimetic robotics, but it's important to be clear about what it is and isn't. This is still early-stage technology. The limitations are real. Cost is the first limitation. Building a robot with this level of biological realism requires advanced materials, sophisticated AI systems, and precision manufacturing. Moya is not a product you're going to buy. It's a demonstration of capability. Durability is the second limitation. motion, the flexible materials, the continuous movement, the embedded electronics. These systems need to prove they can operate reliably over months or years. Industrial robots are built to last decades. Biomimetic robots are still being tested. Power efficiency is the third limitation. Continuous perception, real-time processing, fluid movement. These require power. Current battery technology limits how long a biomimetic robot can operate before needing to recharge. Given these limitations, biomimetic robots will likely first appear in controlled settings. Research labs will continue developing and testing them. Some demonstration and pilot programs will happen in controlled public environments, maybe a specific hospital wing or a dedicated area in a logistics center. These controlled deployments will generate data about what works and what doesn't. That data drives improvement. Over time, as costs decrease and reliability improves, deployment expands to less controlled environments. But this is a multi-year or multi-decade process, not something that happens in the next few years. Biomimetic robots are not going to suddenly replace entire categories of workers. They're not going to be in every home or every business next year. What will happen is gradual adoption in specific roles where human-robot interaction is critical. Healthcare, service industries, research. The value of biomimetic design is that it makes those roles feasible. A robot that moves like a human can work in a hospital without requiring the hospital to be restructured. A robot that responds naturally can work in customer service without creating negative reactions. That's the real significance. Not that robots are becoming more human, that robots are becoming more compatible with human environments and expectations. So here's what we've covered. Moya represents a shift in how companies are thinking about humanoid robots, not as machines that happen to have human shape, but as systems designed to move and respond more like biological organisms. That's only possible because of advances in AI and also because of breakthroughs in hardware like flexible AI chips that can be integrated throughout a robot's body instead of concentrated in a central processor. Moya is still a demonstration, it's still early stage, but it shows where the technology is heading. If you want clear, grounded explanations of emerging technology trends without the hype, subscribe. Drop your thoughts in the comments about where you think biomimetic robotics will have the biggest impact first. Thanks for watching. Catch you in the next one.